so thank you very much, Francois, for this presentation. Let me see how it works. Okay, it works. So what I'm going to present was is the result of a work carried out in collaboration with Alain Gerolimato, who is a former PhD student of Professor Vardoulakis. She is now in Karlsruhe, an institute in soil mechanics and rock mechanics for a tenure track. So the idea here is to present micromechanical expression to allow you measuring the different stress tensors that can arise should you have any valuable reason to venture in modeling granular materials as non-simple continua. I will just, after a very brief introduction, I will talk about non-simple continua. Everybody knows about what are non-simple continua. I will just recall the few features that we need in this talk. I will try to draw a parallel for granular assemblies as close as possible to non-simple continua, and then I will try to bridge the two settings in the end. So non-simple continua, very roughly, there are specialists in this room, so I apologize, but very roughly for me, simple continua as defined by Nold are those for which the degrees of freedom are essentially represented by the classical displacement or velocity field, and for which the constitutive functional is defined in terms of Cauchy stress essentially by the history of the gradient of the displacement. So everything which is out of this framework for me is non-simple. For example, Cauchy continua as soon as the first assumption is released, and for example, second gradient continuum as soon as the second assumption is released. At this point, if you use non-simple continua, there are some odd features that have to be understood and justified depending on the material you are trying to model, which are, for example, the non-symmetric stress, the non-symmetry of the stress tensor, the couple stress tensor, what does it mean, the hyperstress tensor, what is its physical meaning, and so on, apart from, of course, internal length, scale effects, etc. I will try to focus on the first two items as far as granular materials are concerned, especially on the second and third item, because I think that the first one has been, the issue concerning the first one is anyway settled. Still, very briefly, so people working in granular materials, most people accept the fact that a good representation of what is going on at the micro scale can be given in terms of force chains. So the stress is carried by these force chains that run sub-parallel to the principal stress directions. And there is some order in this chaotic behavior given by the fact that, as I said, stress is carried by force chains, and that the contact forces along force chains are almost as well sub-parallel to the principal stress direction. So there is some order, but anyway, it's very difficult to model these materials starting from the micro scale. So with a bottom-up approach, trying to build constitutive model from the micro scale. Some people manage, but it's anyway a difficult thing. So most people try still to use a sort of phenomenological approach, often based on DEM simulation, in which you use some averaging formulas. For example, for Cauchy stress, the most ancient ones, say, were based on stress averages on a REV, starting from the particle scale as a continuum scale. So the first two ones, for example, with averages on the volume or on the boundary. Or you can model the particles as discrete items and use other averaging expression for Cauchy stress based on averages on the surface, or, as the most common ones, as averages on the volume, which are not represented here. Yes. These are the expression that we are using is quite old paper. So these are this sigma is the sigma, this Cauchy stress tensor within the particle. If you model the particle as a continuum, this is the Cauchy stress vector measured along the boundary. It is a very discontinuous thing, of course, but these were the very first ideas that were developed, for example, in this paper or another paper of that period. This is an equivalent expression which, anyway, T is not a stress, but it's a sort of contact force exchanged by contacting pairs. So the question of granular materials as simple materials or not has been discussed, is still being discussed. But anyway, there's a few features on which one can focus if trying to answer these questions. The questions, one of these features to be clarified was the one of about the mean symmetry of Cauchy stress tensor in this kind of situation. I would just like to advertise a paper with Professor Radulakis in which I think we more or less answered to these questions. There are other questions that are still under discussion, which are about the significance and REV average expression in terms of micromechanical quantities for the couple stress and for the hyperstress tensors. There are expressions of these kinds for these two tensors in the literature, which are more or less perhaps a little bit less general than the one I will present, but more or less on the same line of what I'm going to present. So very briefly about the continuum settings, our degrees of freedom will be the standard, those represented by the standard velocity field, and local spin fields in the sense of a micropolar velocity field. So it's not the standard rotation field. We represent this micropolar velocity field in terms of micropolar velocity vector or tensor equivalently. So what I will try to do, I will try to reformulate what we developed a few years ago with Dr. Gerominato in terms of real power instead of virtual powers. I formed an opinion that virtual powers, the beautiful virtual power machinery works very well when the physics is settled. So I'm trying to rewrite essentially the same things in terms of actual powers by using some objectivity requirements. So this linear form, which is written here, is the density distribution for the internal powers, written in a very trivial form in terms of the velocity, gradient of velocity, micropolar velocity, its gradient, and the second gradient of the velocity. Of course, some of this term will disappear very soon. This constitutive transcription is able to receive a certain number of boundary condition and or in terms of that can be expressed in terms of external power as well. So volume forces, volume couples, surface forces, surface couples, and more complex things as land forces on the edge and other complex stuff that is not presented here. And again, I would like to advertise another paper in which we discuss the issues of this natural boundary condition for non-simple materials, again with Professor Radulakis. Sorry. So I will use invariance postulates instead of virtual powers as far as the power density that I have introduced is concerned. So invariance postulates will be proposed here in terms of invariance with respect to rigid motion, which is another way to talk about invariance with respect to the observer, essentially. Two motions, the V prime and W prime motion with respect to their V and W, differ for a rigid motion in the trivial way, where V with 0 and omega with 0 are the constant velocity and angular velocity field of the rigid motion, also in terms of vectors. And you can identify this difference, of course, in terms of velocity, angular velocity, gradient of the linear velocities, but not higher of the gradients of the linear velocity, and not in terms of gradient of the angular velocity for some trivial reasons. So if you ask your power of the internal density to be objective with respect to this superimposed rigid motion, you get some trivial, more or less trivial consequences. That is, your expression for the power density of the internal power will be specialized in a typical form for the stress tensor, Cauchy stress tensor, with respect to the difference between the gradient of velocity and the spin, micropolar spin tensor. Another term is added for the couple stress coupled to the gradient of the micropolar spin, and so on for the second for hyperstress in terms of its coupling with the second grade of the gradient of the display or the velocity. Then with the customary procedure based on the direct sum decomposition, we separate the first term in one concerning the symmetric part and the other concerning the anti-symmetric part of Cauchy stress tensor. So this is the classical, more or less classical, I guess, settings for higher for non-simple materials, as far as you include Gauss-Rat and second gradient theories in a single framework. For granular assembly, so we go back to the micro scale, and we do some simple assumption in terms of what is going on for the grains. So in our theory, grains don't crash, and they just deform at contacts. So essentially what I mean by that is that the mass geometry of the grain is unchanged under the deformation that are the object of our study. Grains, of course, translate and rotate as quasi-rigid body in this sense. And you can easily write for a capillary grain the power of the internal action in the trivial sense in terms of the power expanded by the two respective interaction, Fij of the grain J on the grain I, and Tij in terms of resultant moment with respect to the first to the center mass of the first particles. So the power of internal action between two grains vary trivially in this form with respect to the two respective linear and angular velocities. And of course you can again ask that this power of internal action is objective with respect to a superimposed rigid motion. So we have two motions, the prime motion and the standard motion, which differ by a rigid motion that I try to sketch here by the motion of a rigid frame, say, that we identify by the linear velocity Vij over a fixed point of this frame, and by the angular velocity of the frame, say. So we can specialize the two motion different by this rigid motion in this form, in the V prime form with respect to the standard form. And as soon as you require this invariant with respect to this superimposed motion, you have some consequences that look trivial, because you know already the result in terms of virtual power derivation. And by claiming for the arbitrariness of this superimposed motion, you recover some standard things like action-reaction in terms of forces and couples. Mind that this is couples MIG is not the couples are not computed as a resultant moment with respect to the center of the particles, but can be understood in this form as coupled referred to the point xij, so a totally arbitrarily chosen point. And so they are nominal couples that refer to a nominal contact point xij, which is chosen here arbitrarily with no consequences on the theory. So this is just the idea. So instead of computing couples with respect to the center of mass, you compute them with respect to an arbitrarily chosen point, and you define some nominal contact couples with respect to a nominal contact point. Notice that this approach is hold for grains of any shapes, so it's not restricted to circular or spherical grains. So imagine that you are going to sum, as you integrate power densities on a continuum, you are going to sum this bipolar internal power on the whole assembly. What you get is a first sum on all the contacts in your assembly, which concern the contact forces, scalar multiplied by the difference between their velocity. The second sum is on the contacts and concern the contact couples, nominal contact couples, times the respective velocities, and you have an additional term here which is a little bit more difficult to treat, in the sense that you cannot compute it, and you cannot sum it by contact pairs, but you have to sum it contact by contact for just some algebraic reasons. And by the way, I will not spend time on that, but this is the term which, at least in this work, we identified as responsible for the Cauchy stress tensor not being symmetric in the granular settings. So very briefly, I apologize for going so fast, but this is the expression for the power of the internal densities in this situation. So now we'll try to bridge the two parallel situation, and I will use for that what is perhaps usually called the hypothesis of embedded grain kinematics. So I will try to formulate this hypothesis in this sense. I suppose, I admit, that the power density, the internal power density measured in the neighborhood of a point x0 can be computed with enough precision at the micro scale on an REV centered at x0 by the discrete expression of the power densities, by imposing by forcing the grain to move in terms of linear velocity, a number of velocities as the continuum field imposes. So I will stick the linear velocities to the continuum velocities and the angular velocities to the continuum velocities in this small RIV volume. So the idea is that I assume that these discrete estimates, along with this assumption, provide good enough measurements of the power of the internal density, the density of the internal power, sorry. You are precise need to be about your continuum motion, but it depends on what you want to measure. And if in standard, for example, Weber formula can be retrieved if you just describe the continuum velocity field up to the 0th and first order Taylor approximation with respect to the center of mass of the particle. But if you want to catch some more difficult feature that arise in high shear regions, for example, in shear bands, so you might be in the need of using high order expansion of the real velocity field and perhaps further order expansion of the micropolar velocity field. So let's suppose this is enough to have the hypothesis of embedded kinematics to catch the essential feature we want to measure. The procedure that is applied here is perhaps a standard procedure in which one activates the different degrees of freedom 1 by 1 or 2 by 2, as is the case, for example, for the linear velocity field, for which I activate only the 0th and first order terms, and I set to 0 all the other kinematics. In In this case, we specialize the expression for the power of the internal action density, and as well for the for its discrete equivalent, you get this term that you can work out with some algebra, obtaining this expression as soon as you group the term with respect to the kinematic parameter. What you recover is the standard formula which is currently used for measuring stress in granular materials. In terms of this contribution for the single grain pair, I will call it the microscopic grain microscopic Cauchy stress. So this is the standard averaging formula we perhaps all use when working on that. So I see time is almost over, so I skip on this. As soon as you apply the same procedure for the angular velocity terms, you obtain, stated by the same procedure, a different specialized expression for the internal power density in terms also of granular microscopic quantities. And in particular, you have these two terms, first one and second one. You treat this first one almost in the same way as previously, obtaining what I will call the microscopic couple stress contribution. This is the contribution of couple stress coming from nominal stress couples between grains. But you also have to treat the second term, which can be grouped as in this case and compared to the expression for the microscopic Cauchy stress. In the end, if you group the two, you have two contributions to the macroscopic couple stress, which come from the microscopic couple stress, and for this additional term, which is essentially the first moment of a stress, of a microscopic stress term. This is the permutation third order tensor. So this is essentially the axial vector associated to the antisymmetric part of the microscopic stress. So this is perhaps responsible for scale effect. This is the picture in which I try to sketch the two contributions, the one for nominal contact couples and the one for the moment of the microscopic stress with respect to the center of mass of the center of the REV, and a perfectly similar procedure for the additional, say, higher order velocity gradient term reveal an additional term, which is this one, which is still in the form of a first order moment with respect to the center of the REV of the microscopic Cauchy stress. So this is still perhaps a term which is responsible for same scale effect. Thank you very much. There is no real contact point. It's the action of F of the J grain on the I grain. The contact point you can choose whatever you want.
There is a constant for this.
Of course, you can specialize it to the particular grains that you are going to.
For monolateral below, if the distance is too much, maybe there is an
you can in the general case you expect to have unilateral mechanisms, but this is quite general, and this is not specified in this approach, I would say. Sorry?
Fundamental question of this kind of approach. What is the real motivation? I asked myself a couple of years before, I don't think it's the response. In fact, is a granular assembly a develop such kind of conviction theory. What is your point of view? Do you think that experimentally or empirically you can access to such kind of non-classical forces or local movements?
I'm not a perfectly well-shaped opinion on that. I'm just saying that if you want to answer to these questions, you might use numerical simulation, discrete numerical simulation, but then you have to find a way to measure these higher the stresses and couple stresses to see how are they responsible for a certain behavior or not. So this is just a technique, a toolbox safe to measure this quantity, to see if these are measurable quantities, relevant quantities, and so on, and perhaps a numerical simulation of discrete numerical simulation of.
That's an important work. Do you have the idea? We can discuss the work or later. So ideas, what to do now, for instance?
What I want you to do is now to go to the constitutive part. So to frame a little bit what can be said in the constitutive part, still based on simply on objectivity requirements, because I think this is the more flexible tool to frame any possible situation that you can encounter. Yeah.
So maybe I cannot resist to think. First of all, not only simple or non-simple, you can say materials which were understood by Husserl and those which Husserl did not manage to understand, while Germans have understood them. This is polemical against people who are dead. In my opinion, for advancement of science, one has to be clear. Second, I agree nearly with everything which was shown here. Maybe you should talk a little bit with Anik Misra, because what you are planning to do is find in some papers by Anik. The crucial point, which is included in the theorem by Pierre Sepecher and Catherine Pidelli, is that when you have highly inhomogeneous microstructures, these formulas prove that the energy in higher gradient terms is comparable with the energy of lower time. So the crucial point is that all this machinery, I see something which is not completely persuading, because with these formulas, with the same sigma in both formulas, boundary layers are smaller than representative elementary volumes, so the continuum model doesn't apply. If you have highly inhomogeneous constitutive equations at micro level, then this identification shows you that at macro level you really need higher gradient continuum. So, to your question, there are one theoretical answer given by the general theorem in gamma convergence by Sepecher, and there are important numerical simulations which for a slightly more regular grades are available by Anil Bachmann. So I think that this approach is fruitful. So I agree with many other people. Okay.